Good morning, everybody. My name is Faith Dukes. I'm Director of K-12 Programs here at Lawrence Berkeley National Laboratory, and we're excited to have you join us again for research here at Berkeley Lab and a look at STEM careers. Today, we are talking about research in space, and we're taking an energy storage field trip with some of the scientists here at Berkeley Lab, SLAC National Laboratory, and NASA Ames. And we look forward to having a lot of conversation around space, energy storage, and research at all of the laboratories and organizations. And today, I'm actually going to be joined by a guest. So I'd like to invite Elvira, who is an Experiences in Research intern here at the laboratory, to join me on stage. Elvira is not only a science communicator, but she is also an intern on the K-12 team. If you've seen any content from us lately, it's from Elvira and her partner Myra, who've been working on a lot of the social media content here. Elvira is an incoming college freshman excited about studying design, technology, and communication. So Elvira, welcome to the virtual stage, and thanks for being my co-host today.
Thank you for the introduction, Faith. I'm super excited to be here and to introduce Dr. Noël Bakhtian. She's the founding executive director of the Berkeley Lab Energy Storage Center, with more than 200 researchers to accelerate energy storage solutions in response to climate change. Research.
Really excited to be here.
Awesome. Before we get too deep research areas, would you mind defining energy storage and why is it an emerging field for technology and science?
Sure thing. That's an interesting question. So I kind of see energy storage as something like a time machine. You're able to store energy for when you need it at a later time. So it's separating when you create the energy from when you want to use it. Sometimes a second later, sometimes a year later. And a really simple example I like to use is solar panels are an exciting clean energy technology. They use the sun's energy to produce electricity, except we know the sun doesn't shine at night wherever you are in your location. So you can use energy storage like a battery to store that energy and then release it when you need it. And there's all kinds of different ways to store energy. You've probably been learning in your physics classes about something called potential energy. So like when you roll a ball up a hill, there is potential energy related to the gravity. Well, guess what? It's that potential that energy storage takes advantage of. There's actually a type of energy storage tech called pumped storage hydropower, where you literally drag water up a hill when you have excess energy you want to store. And then when you want to release that energy, you just let the water flow back down the hill and it turns a turbine using that energy, which creates electricity. So batteries use something called electrochemical potential, which is a different kind of energy. And then there are other types like thermal energy storage, chemical energy storage, etc.
Awesome. That's such a great way to explain it. Before we get too deep into research areas though, would you mind defining energy storage? I know you did it a little bit. And why is it an emerging field for technology and science?
Oh, you know what? I actually don't consider energy storage an emerging field. Energy storage goes back over 100 years. I mean, even lithium-ion electrochemistry, which is the basis for all the lithium-ion batteries found in electric vehicles and all over, was actually invented at Berkeley Lab in the 1950s, so like 70 years ago. But the need for more energy storage is so great in the future for climate change and resilience purposes that there are thousands and thousands of people around the world actually working on advances in energy storage. So we are working on advances, thinking about how do we make batteries smaller or more energy dense, or how do we make them cheaper so they're affordable to all or for new uses, or how do we make them safer, or how do we create new chemistries so we can avoid using elements and materials that have supply chain sensitivities. So it's still a very exciting field to be in.
Awesome. To help a broader audience learn about energy storage and maybe get some students into it, your team has created energy storage field trips. Could you tell me a little bit more about them?
Yeah, absolutely. So I'm going to tell you about the Energy Storage Center in a few minutes when I'm showing my slides. But what we've done at the Berkeley Lab Energy Storage Center is we've partnered with SLAC Lab, and Johanna is here as a speaker today too. So we've partnered together to launch this new seminar series that's all about taking virtual field trips to explore the important and exciting role that energy storage plays in the world around us. It's open to everyone, so I hope that you guys will all join us. You can sign up at our website, which is secretlifeofenergystorage.lbl.gov, and I think that's going to be in the chat box soon too. And our first virtual field trip in March was actually to the International Space Station, which is the national laboratory orbiting Earth up in space. And Faith and I actually got to talk to an astronaut up in space. Her name is Kayla Barron, about the importance of batteries to their mission in space. And we recorded it, of course, and today you're going to get to hear from Kayla as she's floating around the space station. So with that, I'm going to stop talking and let's hear from Kayla. So let's take a break and blast off and take a quick field trip to the ISS.
3, 2, 1, 0. Ignition. And liftoff.
Laboratory in orbit, the International Space Station. Vehicle is pitching downrange. And that's the call we want to hear. Good performance on that first stage so far.
T plus 30 seconds, Captain 9, powered by 9 Merlin 1Ds. Pushing Dragon into low Earth orbit on the way to the International Space Station.
Power and telemetry nominal. Station, this is Houston. Are you ready for the event?
Houston, this is Station. I'm ready.
Kayla, greetings from Earth. We are so honored that you've taken this time to talk to us. I'm Noël Bakhtian from the Department of Energy's Lawrence Berkeley National Lab, where I lead the Energy Storage Center. Can you talk us through how the International Space Station is powered and why you need energy storage?
Yes, absolutely. Energy storage is vital to what we do every day on the space station, and it is really important as we think about future exploration on the moon and Mars. We're actually powered by solar arrays. We have 8 power channels, 8 really large solar arrays that send power onto the space station when we're on the sunlit portion of the Earth, but we're also charging batteries that entire time as well, so that we're in the shadow portion of the Earth, we can draw power from those batteries. So those heritage arrays, those 8 big solar arrays, are what we've been using to power the space station for the last 21 years. And we're in the process of upgrading that solar array system by adding some augmenting arrays. We call them IROSAs because we love our acronyms. You might too at the National Lab, but it stands for ISS Rollout Solar Arrays. And basically they're these solar arrays that we're installing at the base of our existing solar arrays to provide additional power for new requirements and to account for the degradation of those the heritage arrays over time.
It's almost like you have a microgrid up in space. That's a great parallel to our power grids on Earth. As we're working on transition to clean power by 2035, that requires adding in a lot of clean energy sources like solar and wind power, which are intermittent. But energy storage is a major part of that solution space. We'd love to learn more about the energy storage system you've got on the International Space Station, though. What kind of system is it?
So originally we had 48 really big nickel hydrogen batteries that are stored outside on the truss of the space station. And from about 2016 to 2021, I think, we worked on upgrading all of those. So we actually removed the heritage batteries and replaced those 48 batteries with 24 lithium ion batteries. They're huge. They weigh about 400 pounds on Earth. So they're pretty big beasts to manage on a spacewalk. But those were all upgraded. And so those allow us to store power that we're producing when we're in the sunlit portion of our orbit. So usually we use about 40% of the solar array capacity while we're in the sunlit portion, and the other 60% of that energy is getting stored in those lithium ion batteries for us to draw from when we're in eclipse.
Elisa, do you want me to start my my presentation?
Yeah,
okay.
that would be great. Thank you so much, Noel. We'll come back to the video after. Thank you.
Perfect, absolutely. So hey everyone, as part of this event, we're going to be sharing a little bit about our career paths. And so I'm up first. And so let me share my screen. So this is my career path, my STEM path, everything from Star Wars to Mars to oceans and batteries and beyond. So let's start with high school for me. I really loved my math classes and most of my science classes. I didn't have any engineering classes in high school, so I didn't quite understand what engineering meant yet. But looking back, I loved sci-fi books. I was always surrounded by airplanes because my dad was a pilot and my mom and her family worked for TWA, which was an older airline. And we went to air shows and lived in Florida so we could see the space shuttle contrails on launch days sometimes. And I was pretty obsessed with anything aerospace related. My dream was to be an astronaut. So the fact that I turned out where I did is actually not too much of a surprise now that I look back. But on the way here, it seemed like I was hunting for something big. So one of the most formative experiences I had was going to a summer camp called Summer Science Program, or SSP. So for those of you who are sophomores or juniors, look into this. The link is up at the right. I actually spent 6 weeks with a class of about 20 kids tracking asteroids with this huge telescope, and they taught us everything we needed to know. They were teaching us college and grad school level science and math to actually be able to calculate the trajectories of the asteroid and submit our results to the Harvard-Smithsonian Minor Planetary Center. And I ended up being on the board of trustees for this organization for years after, and we actually launched many new different science curricula through SSP, like in biogenomics. So check it out, even if you're not a space nerd like us. And then came the big college decision. And that's when I decided to try out engineering, which I later learned is just applying science to solve problems to help people, which I think is a pretty cool thing to do with your life. So school, I was in school for a long time. I was in school until I was the day after my 30th birthday. And I ended up doing mechanical engineering to get a really strong foundation in things like materials and thermodynamics and fluid dynamics. Then I got a fellowship to do a master's degree at the University of Cambridge in England. And then I spent 5 years at Stanford and NASA, really living the dream and geeking out on rocket science. So I'm going to show you a little bit of what I worked on. So in England, during my first master's, I was helping some zoologists at Oxford who were trying to figure out what this weird special flap of feathers at the leading edge of bird wings were. And I had my own wind tunnel that I was experimenting with, and I was doing lift and drag tests at different configurations. And let me tell you, though, that no birds were hurt in the formulating of this thesis. But what I discovered is that the flap of feathers actually acts as a tripping device to stop the bird from stalling out when it comes into land at high angles of attack. So I got my first ever publication out of this, and actually the drone community was very interested in this research. And then I finally achieved the dream of working at NASA during my PhD, which was at Stanford, just 20 minutes away from NASA Ames Research Center. And that's my team there on the left in the Advanced Supercomputing Division. And ta-da, this was my PhD thesis title. Don't worry, I had no idea what those words meant when I started my PhD either. But basically what I ended up doing is using my fluid dynamics education to come up with a new technology to land humans on Mars, because we don't have the technology to land a mission there bigger than the current rovers we're sending out. And basically what this technology is using the jets as flow control devices to manipulate the shock wave in front of the capsule to help it slow down with less fuel, which is a big problem in space, too much fuel. So I was doing a lot of coding and running optimization algorithms on the NASA supercomputers. And by the way, if you think that I didn't put Marvin the Martian in my thesis dissertation defense slides, you are absolutely crazy. So after my PhD, I decided to learn more about how science policy gets made in government. How do they make decisions like, let's shut down the space shuttle program, or what year are we going to go to Mars? So I took a position in the US Senate in Washington, DC as a fellow, and we did lots of things like developing bills, turning them into laws, and also had some fun meeting folks like Bill Nye the Science Guy and Charlie Bolden, who was the NASA administrator at the time and a former astronaut. But something crazy happened. During my year in Congress, no one really wanted a space policy fellow that year. So I actually took a position doing something I knew absolutely nothing about, which was working on energy and environment. And that's the year that I learned about climate change. And that's the year that climate change scared the bejesus out of me. So I decided to stray a little bit from my aerospace and dream of being an astronaut to save the world. I stayed in DC a few more years to work on it. And I ended up going to the Department of Energy headquarters and running the Wave Energy Prize for a year. And then my next job was I got poached by the Office of International Affairs at DOE, who actually asked me to start a program on something called the Energy Water Nexus. And that's just all about the interdependencies between energy and water. So I learned a lot about how you do international affairs, and I ended up going to China to negotiate a $50 million US-China Clean Energy Research Center on the Nexus, brought in the Israelis to the US to talk about desalination for the first time, which ended up turning into, I think, the US-Israel Desalination Prize, and had a lot of other really cool international experiences. And then I ended up at the White House under President Obama as a senior policy advisor for energy and environment, working under Dr. John Holdren, who is the president's science advisor at the time in the Office of Science and Technology Policy. And had a lot of fun there too. I went to the science fair, of course, and found the One Rocket project, as you can see on the right. And we took some breaks as well between the crazy work. So then after the Obama administration, I decided to head back to Department of Energy, but this time in the National Lab System. So you guys have probably already learned that the Department of Energy owns 17 national labs across the country that you can see there on the map. It's about $30 billion a year that are spent across these labs on doing research. And so my first job, I found myself in the senior leadership position of a $1.5 billion national lab, the one in Idaho, that focuses on nuclear energy and cybersecurity. And I got the chance to run a consortium that brought together the national lab with all of the public universities across that part of the US. And so we had so much fun creating collaborative programs and thinking about how these 5 institutions could be stronger together than the sum of the parts. And then one day I got a call from Berkeley Lab saying that, hey, we want you to come out and help us stand up a new clean energy science and technology center on energy storage. Took them a year to convince me, but I finally made it out here. So here I am working at an institution that's had 14 Nobel Prize winners, and I've got over 200 really passionate folks doing research on energy storage across the lab to solve the hardest problems in climate change and resilience. And then, of course, I get the fun of being able to talk to you guys, our future brilliant scientists and engineers. So that's my path. I'm going to stop there and can't wait to talk to you guys more.
Thank you for that super unique and inspiring journey. And we're going to shift gears and go to astronaut Kayla Barron, who during her interview also explained how she got into STEM. So we're going to share her answer next.
And I were so curious about what inspired you to be an astronaut? What influenced your decision to take a STEM path?
Yeah, you know, I was really lucky to grow up in communities that had strong science and engineering industries. My dad works in the nuclear power industry, and my mom is a math whiz. And so growing up at home, I was always really encouraged to maintain my curiosity about the world around me, and that meant for me an interest in science and math and ultimately engineering. So I was really lucky that I was surrounded by people who didn't think my questions were annoying. My parents always entertained my questions about the world around me, which was really encouraging. And I had some fantastic teachers who really kept me going. You know, as you know, as we all know who have studied STEM fields can be pretty challenging, and they're tough concepts. And as a student with a lot of heavy course load, you know, it can be tough to get through those classes. But I had some fantastic teachers who really encouraged me to stick with it and helped me understand that that passion for the world around me could be best applied by studying engineering. And I'm really glad I followed that trajectory. For me, I've always been inspired to work on mission-driven teams with awesome human beings. And so that drew me to join the military and become a submariner, and ultimately inspired me to apply to be a part of the NASA team, because I was so inspired by the things that we were doing. I just wanted to be a part of that team. And I'm really lucky that for me includes the opportunity and honor of working aboard the space station for 6 months.
Awesome. And now that we've got an introduction to energy storage and a look inside of the International Space Station, I'd like to invite our additional panelists to introduce themselves. First, we have Dr. Johanna Nelson Weker, who is a lead scientist at SLAC National Accelerator Laboratory. Her research focuses on synchrotron-based X-ray characterization of materials and systems far from equilibrium, and spans topics including electrochemical energy storage, catalysis, and additive manufacturing. And after Dr. Nelson Weker's introduction about her career path, we will have Dr. John Lawson. He is currently the group lead for computational materials modeling at the NASA Ames Research Center in the Intelligent Systems Division. Dr. Lawson and his collaborators have worked on a range of materials, including polymer composites, high-temperature ceramics, shape memory alloys, nanosystems, and materials for advanced energy storage. Welcome, Johanna, and we're super excited to learn about your work.
Thank you very much. So let me talk a little bit about my career path. I assume you can see the slides. I am a lead scientist at SLAC National Accelerator Laboratory, SLAC, or we call ourselves Slackers sometimes. Like Noël suggested, it was Department of Energy National Lab. We get our funding from the DOE, but we're operated by Stanford University. And if you know the San Francisco Bay Area, this is a picture of the Bay, and Stanford University is here. And then SLAC is about 2 miles from Stanford University. And we have visible from the highway, 280, you can see our very long accelerator. And so at SLAC, I work at the Stanford Synchrotron radiation light source. And basically what it is a giant building-sized X-ray machine. So it produces a ton of X-rays, and we use those X-rays to characterize materials. So how did I get here? Well, a little bit about myself. I was born and raised in Gettysburg, Pennsylvania. Gettysburg is well known for the Civil War. It was the longest, bloodiest 3-day battle of the Civil War. We also have a lot of iconic covered bridges. My very first job while I was a high school student was working at an ice cream shop, serving ice cream to tourists. We gave a 10% discount if you were in costume as either a Civil War reenactor or someone from that period. When I graduated, I went to Muhlenberg College. Muhlenberg is a small liberal arts college, undergraduates only. It's in Allentown, Pennsylvania, and I double majored in math and physics. Why did I double major in math and physics? Well, because I liked those classes. I really didn't think about what job I would get with this major. I just knew I was good at those classes and they were fun to be. So that's what I did. Maybe that was not the best choice, but that's sort of the reasoning I had when I was 18. One of my most memorable experiences and really got me into physics as an experimentalist was my chance to work at a robotic telescope that Muhlenberg College was setting up. So they had just built this telescope. The telescope was in Australia, but I was working in Pennsylvania, operating the telescope during the day while it was nighttime in Australia. And I was able to do sky surveys using this telescope. And that was my first real introduction to true science. After college, I decided that I wanted to go to graduate school. One of my main influences on why I wanted to go to graduate school was my older brother. He had gone to graduate school for physics, and my older sister had gone to graduate school. So it kind of just seemed like something we did in my family. Why I decided to do physics rather than math, since I had a double major, was physics seemed a lot more approachable. Math seemed kind of terrifying to do in graduate school. I thought, oh, as a mathematician, I'd sit, alone thinking mathematical thoughts by myself, and physics seemed a lot more people-oriented. So I chose physics. Things that I didn't know before going to graduate school. First of all, I didn't know what field in physics I wanted to study. I think I said I was going to do high energy physics when I wrote my essays. Of course, I didn't do that at all. I also didn't know what a national lab was, even though I ended up a few years later working at a national lab. And I had no idea what a synchrotron was. So I was really pretty naive going into grad schools. I just made the decision to join a group because the research group seemed really nice. They were working on a diverse set of problems. They were applying X-ray microscopes to look at biological materials, and I liked that intersection between biology and physics. And so that's why I joined the group, and I ended up going to Berkeley Lab to take all of my data I took the highest resolution image with X-rays on a biological sample at the time. So that's sort of my thesis, was taking images of yeast cells. And so then after that, I actually went to my current position. Now I actually work at SLAC, at the Synchrotron. So I stayed with Synchrotron physics, but now I've moved to looking at batteries. And so I use my X-ray microscope still, and I take pictures and movies of batteries. These are just a few examples. We can look inside a commercial battery. So this is what's called an 18650 battery, but it's a little bigger than your standard AA battery, and we can see all the layers inside. We can also look at the chemistry, and here we have color just distinguishing between the two chemical states of this cathode inside a working battery. And so we can use X-rays to look inside the battery as it's working. And also, I don't just do batteries, we also do 3D metal printing. So this is a movie of us taking a laser and printing and watching what's happening with X-rays. And then finally, I just want to end that, science is done as a team. We're not individuals. We're not sort of these geniuses working alone, but we work together as teams, and it's really the team aspect of science that really gets me up in the morning. It drives me. It's that collective discussion about, what are the problems? How can we solve them? So I'm really grateful for my team of scientists that I work with at SLAC. So thank you. And now I'm going to hand it over to John.
Great, thank you. So it's great to spend a little time with you all these future Einsteins. You guys are the future. You're gonna build the future. You're gonna come up with amazing ideas that are gonna change the world. So it's great, to be able to engage with you guys this morning. So my name's John Lawson. I'm at the NASA Ames Research Center, which is in Mountain View, California, which is actually not too far from Stanford, south of San Francisco. A lot of people don't realize there's a NASA center in the Bay Area because there's so much going on here, Silicon Valley, Lawrence Berkeley Lab, other places that sometimes it gets a little bit lost. If you go to other cities that have a NASA center like Cleveland or other places, everyone knows about NASA, but we're a little bit lower profile, I guess, but we are a significant center. So here you can see that we're actually, a full campus. We're the size of a college campus. You can see the picture at the top, and probably maybe 5,000 people, including researchers and support staff there. I'm in the Intelligent Systems Division, and I'm the group leader for the Computational Materials Group. So we try to understand, we use supercomputers, such as the one on the bottom there. That's a picture of the NASA Advanced Supercomputer. This is one of the top 10 supercomputers in the world. We have like 500,000 CPUs that can be used all together to run these massively parallel simulations to do all kinds of problems that NASA's interested in. I lead an interdisciplinary team with 20 PhDs that include computational scientists, include physicists, chemists, engineers, data scientists, and others. And I think that's kind of a trend recently, say in the past 5 or 10 years, is a lot of those traditional disciplines that are in science, chemistry, biology, physics, different engineering flavors and all that. They're all kind of merging these days, and you're getting a lot more multidisciplinary or interdisciplinary teams coming together that pull people from different disciplines. So you don't have these disciplines that are siloed like they were traditionally, like physics, chemistry, biology. But now you're having like biophysicists or biochemists or whatever, chemical physicists, all these things. And so that, I think, for someone like me is one of the exciting things, because not only do you get to learn about the discipline that you trained on, but then you get to work with all these other amazing experts and learn about their fields as well. So you're constantly learning, which really makes it an exciting, dynamic environment. Next slide, please. So a little bit about me. So I grew up in a small college town in South Carolina. My dad was a university prof. He's actually a biologist. When I was young, I really didn't have much interest in space, or computers. So I would have never guessed my career path. I was actually reading a lot on different things, history, English, novels, interested in sports, played a lot of tennis and soccer. These are sort of my main interests. Science was something that I was kind of interested in, but that was just one of many things. And so I think, if there's a common thread through all this, I think is that, if you could have said, how would I have predicted, or someone would have predicted I would have ended up where I am now. And I think that the reason you might have made that prediction is just curiosity. So I think that, an essential thing for any researcher in any field, whether it's, history or English or physics or math, is you must have curiosity about your discipline, but then other things too. So I think people that are the more curious you are, the better, the more you can learn and the more you can make contributions to different areas. So like I said, I didn't really think too much about space. Of course, everyone as a kid is interested in astronomy, and I was, one of those, had a telescope as a kid, but didn't really think or know too much really about NASA, like other people who that was their career path. Same thing with computers. I actually didn't learn how to code until I was a graduate student. So that was, well, that would have been a surprise too. If you'd asked the younger me, where would I end up? I think a key thing for laying the foundation for my career was that in high school, I had terrific math and physics teachers. And so I really nailed those skills in high school. And so I think if you're really strong in math and science in high school, it's going to make college much easier for you. I mean, was certainly the case for me. I mean, I really kind of coasted through a lot of college physics because I had that great foundation. And that high school education probably really laid the foundation for my whole career. So again, really mastering those skills is important. My current job path, so I studied at Brown and Clemson University. Because I was fairly interested in a lot of different topics, I had some trouble picking a major. And at the end of the day, what I decided was most important was I wanted to work on ideas, developing new ideas, and that would have a positive impact on society. That was the most important criteria. And what field that wasn't quite as important, whether it's physics or engineering or some other field. So it turned out that physics fit that criteria, although it's not necessarily the only path I could have gone into. Research topics that we work on: batteries for electric aircraft, thermal protection materials for space vehicles. I did go to grad school, like I said, and I did a postdoc actually in Italy, which this sort of level of experience is really important to be a career physicist. Italy was amazing. So that's another thing about being a researcher. You get to go to amazing places. So I spent 2 years. Actually, my office was just a walking distance from this castle on the ocean on the coast of Italy. Ate a lot of Italian ice cream, the famous gelato. And so, I had a great time. And of course, as a researcher, we go to conferences all the time, et cetera. Some of the things we work on these days are computational modeling, like I said. So, we do everything from modeling proteins. So here's a molecular model of a protein on the left here. So, and one defect in a complicated structure like this can cause diseases like cancer. And so, of course, cancer is a major problem on Earth. But when you put people like astronauts into complex, harsh environments, they can definitely acquire genetic diseases and mutations that can lead to cancer. And so something we try to understand is how do defects in complex structures like this lead to diseases like cancer? And then can you design on a computer a drug that can mitigate that? We're also interested in energy storage, of course. We're interested in so NASA is interested in airplanes as well as space. So can we design batteries for electric airplanes? So here's an example of a NASA electric airplane called Maxwell with all these propellers on the front. And so we're using computer simulations to try to design advanced, high energy storage. You really need high energy storage batteries for airplanes, much higher energy densities than say for cars. So much more demanding requirements for airplanes than for cars. So a lot of these, I think are not only important for NASA, but they're important for humanity. I think really the grand challenge problems for our century are energy technology, like storage, for example, to save the climate because of the climate change issue. And also I think, personal and what we call virtual medicine. If you can design drugs, say, on a computer without having to go into the lab and test like 1 million candidates, but quickly screen things on a computer, you can potentially save millions or tens of millions of lives every year. So I think, computer simulations, I think, can potentially open the door to help making progress in both of these areas. And with that, I'll stop.
Thanks, John, and thanks, Johanna and Noel, for starting us off with those wonderful introductions. We've got a lot of reactions that we can see in the webinar. And we'd like to invite all three of you back on to the virtual stage now to begin our Q&A. So John and Noel, thanks for joining us again in those very interesting career journeys and pathways and more introductions to energy storage. You have a few questions in the chat box that are coming in, but we would love for everyone to start to put in those questions either in the Q&A or in the chat. We'll get to them, and I'll pass it over to my co-host Elvira, who will start us off with questions that we have for the panel.
Yeah, we wanted to start off with the question, what do you see as the biggest connection points between energy storage and space? And we're going to start with Johanna and then go to John and then Noel.
Yeah, so I think as we move forward, our main goal in making things green is first to electrify everything. And so like Kayla said, in the International Space Station, they have solar panels, so it's an easy connection to have energy storage with those solar panels. And anytime you think about your energy storage needs, they're different depending on the use case that you have. And so putting batteries or any different types of energy storage in space is very different than what you would want to do as a ground-based. So things that you're more concerned about in space is safety is a big issue. You know, there's no way to run away in space. And size and weight matter a lot more since you have to get everything up out of the atmosphere into space. And cooling is also a hard thing to do in space because you don't have the air around to cool things naturally. And then finally, radiation is a lot different because you don't have the atmosphere protecting us from the radiation in space.
John, do you have an answer to that question?
Yeah, sure. Yeah, so obviously space is different than the Earth. So therefore, you know, technologies that we develop on Earth, you know, you can't necessarily expect it to work in space. So you have to be modified. One example is, say, the Mars rovers, you know, run on batteries. So they have solar panels, but of course on Mars you have nighttime. And so then you have to store the energy, but it's super cold on Mars compared to the Earth. So actually, you know, NASA researchers had to redesign the electrolytes for the batteries so that they wouldn't freeze, because if your electrolyte, which is a liquid, freezes, then you're out of business. So we had to develop, you know, special electrolytes that could go down to those very low temperature. Also, as Johanna mentioned, you know, if you're in the space station or you're in empty space, or you know, you have problems with radiation, so you can have a heavy particle can come in and damage your device, whether it's energy storage or your photovoltaic. So you're often in these harsh environments, either in terms of like temperature differences or radiation or non-radiation. So everything has to be sort of reconsidered in these different environments, more challenging environments.
John and Johanna are the real experts. And I just started thinking about energy storage and batteries like 2 years ago. So I'm pretty new to this. I'm like a newbie in this space. But, you know, when I started thinking about truly what is the essence of energy storage, it kind of blew my mind when I realized when I think about electricity, I just think about plugging my lights into the, you know, to the wall outlet, and all of a sudden I've got energy. But then I started to think, well, I can't always plug things in. That's why when you want to take your car out, but you don't want it running on gas, you want it running on something more clean. Well, batteries help you be mobile. And so then when we were doing this thing with the astronaut, I was like, oh my gosh, it's like a big old car in space, or, you know, kind of like a microgrid. They had to create their own thing because they can't just plug into the Earth anymore in the grids that we have here. And so that kind of like shifted the way I thought about the power of energy storage. I think John and Johanna touched on a lot of the good stuff already. I think about all the other fun things that we want to do in space too, not just the International Space Station, which is in low Earth orbit, but also going to other planets and potentially maybe putting a base at the moon one day, which I think is kind of where the Artemis program at NASA is going. And so energy is going to be needed for all of these activities. And so the question is, do you need storage? Usually, yeah. So that's why it's important. And then one more fun thing that Kayla actually taught us is that the International Space Station is actually a living laboratory. They actually do science. They're actually doing 3D printing and stuff like that. And so we can actually think about how do we change our understanding of materials by doing some of our experiments in space at the ISS, et cetera? And how can that help us come up with better materials for the energy storage we want to do?
Awesome. There are a lot of questions coming in, so we're just trying to make sure we get to every single one or as many as possible. But I want to ask two quick ones that came up during both Noël and John's talks. One for John, how many flops and is the supercomputer on the campus of Ames Research Laboratory?
No.
Yes, the supercomputer is on site at Ames, but of course, with computing today, you don't have to be, on site to use it. So we have a lot of remote users. So in fact, in my group of 20 people, there's like 15 people or so that are across the country that use it remotely, and that's not a problem. So it is on site, but that's not essential for us to use it, and we make heavy use of it.
Awesome. And Noël, a quick fun question. What was it like to meet Bill Nye?
Oh my gosh, it was a long time ago now, but kind of the impression I came away with is he is so humble. And it made me to start to think, like, why is Bill Nye famous? It's because he explains science really well. And so I've tried to bring that with me as far as thinking about how do I communicate like all these scientific topics to everyone, because everyone should be able to understand it and make it a more democratic topic.
Awesome. And we're going to move on to some Q&A questions. So Sherry in the Q&A box asks, how can technologies developed for astronauts in space also help people on Earth? Does anyone maybe have an answer for that, or we can start with John?
Sure. Everyone always hears about, the different NASA spin-offs, right? NASA research leads to all kinds of benefits on Earth as well. And a lot of times when you have to sort of push the requirements of a technology like batteries to more expansive regimes, it benefits things on Earth. So if you can make batteries that can withstand harsh environments and bigger temperature fluctuations, and that can give you a more robust battery, for example, that you can use on Earth as well. If you can understand, things like how putting people in harsh environments affects their health, well, that might help you deal with a similar, say, genetic disease on Earth. So a lot of times, because space is so challenging and the requirements are so high for the performance, that by meeting those challenges, which might be too much on Earth, but you have no choice in space to meet these challenges, right? Because otherwise you just have to stay home. So you have to get these high performance goals, or else you stay home. But then you can utilize that on Earth, whereas you might not have pushed the envelope as much just for an Earth application.
And I'll give a specific example of that, if I may, John. We learned this from Kayla too. You guys heard Johanna talking about safety and how the need for safety is more important in space, because if there's a little fire or something, you can't just run away. And so something that happened when they were developing the batteries for the International Space Station is they actually had to develop even more protocols and more technology solutions for something called thermal runaway, which is actually like a catastrophic event that sometimes happens with batteries, which is when they get warmer and warmer, and then there's a bunch of chain reactions that go on and the thing catches on fire, basically. And so they created this new technology for controlling that. And that's the kind of thing that might be useful once we get the cost down at scale for batteries here on Earth too.
All right. Thanks, Noël, and thanks for giving those specific examples. I'd like to start back with Johanna about working at a national laboratory. You talked about the different, and John as well talked about the different fields that people are in, and they're very much interdisciplinary in order to solve the different problems that we have. So how is working in a government laboratory different from working in maybe a university laboratory or a private industry? And what do you think about in terms of their support and funding? So how do we decide on what we work on, and how is that funded for government versus private industry or university?
Yeah, that's a big question, but there are some fundamental differences between working at a university and a national lab. One of the biggest things is when you're working for the national labs, you're working more collectively and collaboratively together. When I'm working with a team, I don't work with just other physicists. I work with a lot of chemists and engineers, and it's all of our collective backgrounds that really help us drive the solving the problems My specific job actually is to run the X-ray microscope for outside users. So I have visiting scientists that come every day to use our microscope because it's pretty unique, and there's only a few in the world. And so I get to learn about their science that they're doing when they're coming to my microscope, as well as doing my own science. So I think that's really interesting for me because I get to learn about other fields. And I have to say, when the dinosaur people come, that's always the best week ever.
Awesome. A question that we've been thinking of and some students have been asking is, what's one challenge that you faced in your career and how did you solve that or move past?
I can answer that one first. As I said in my introduction, I went to a small liberal arts college for my undergrad. And that is not sort of the normal track to graduate school, because I took about a third less physics and math classes than my other fellow students in grad school took when we were going into grad school. So my first year in graduate school was very difficult. Just the challenging the challenging classes were hard for everyone. And then I had such less background compared to all of the other students. I could read and I could write better than them because I had this liberal arts background, but the fundamental science, I just didn't have that background. And so the way I overcame that is basically make friends and have a support group that first year in grad school, and homework. Believe it or not, you still have homework in grad school. Homework became sort of a social aspect of we'd all get together and we'd all work really hard on these problems together. And by the end of the week, when you were finished with your homework, everybody understood it. But it was, if I had tried to do that on my own without that support, I would have never survived my first year.
Awesome. John, do you have a specific challenge that you face?
Well, I think probably a challenge that most people have who are career researchers is actually getting into a stable job, stable position. Because after you finish your training, then you do like a postdoc or a series of postdocs, and these are usually short-term positions. But making the jump from these short-term positions to something more long-term can be very challenging. And so I think, doing a lot of the career things that no one ever teaches you in school, unfortunately, like how to network and how to, reach out and make contacts with people and, keep your connections alive with professors, even in high school teachers, and then, your undergraduate teachers as well, and then graduate students. Keep your network active, keep people informed about what you're doing, and then you can plug into that network when you need help, like say getting a job. So these are things that people we're not usually taught, especially as scientists, but I think things like that can be really important and pay off for you later.
Awesome. That's been a thread throughout most of these talks of making sure you have the network, keep your relationships going and sustained, making sure you're reaching back to those people who have had an influence on you. As we transition to another question, we want to talk about a little bit of climate change or climate mitigation, actually, and pollution. One student asked about, how is your work actually supporting, and Noel, we talked about the Energy Storage Center came out of thinking about climate change. So how is the work, helping to mitigate climate change and support our environment? And how are we making sure that things like energy storage containers, like batteries, don't pollute the environment?
Is that a question for me or just for everyone?
Yes, Noel.
Oh, sure. Yeah, so I think about it through several lenses. So for instance, when you talk about climate change, we're talking about, greenhouse gases and these emissions that are up in the atmosphere because of human activities, but not completely human activities. So on the NASA website and basically anywhere, you can see the pie chart of where these emissions come from. And a huge portion of them actually come from transportation, for example. So that's why, as we're trying to move away from oil and gas in our cars and our trains and our freight trucks and our airplanes, et cetera, energy storage can come in handy, like I said, because you can't just plug into a clean energy grid. You're out and about. So that's where electric vehicle batteries come in, and hydrogen, and all kinds of things like that. So there's the transportation side of it. And then think about buildings. Think about, your house and the commercial buildings and your university buildings, your campus buildings. All the buildings that we're in actually take up a heck of a lot of energy every day. And so how are we decarbonizing our buildings? And, at Berkeley Lab, we're actually working on some cool new technology called phase change materials, which is basically creating a big, using your walls of your buildings basically as a battery and storing thermal heat in the walls of your building. Instead of having like a Tesla Powerwall, which also works as well, but we're thinking about different kinds of costs and scale. And then there's the grid. There's cleaning the grid. How do we put more solar and wind and clean energy technology on the grid to avoid natural gas plants, et cetera? And that's, again, where batteries need to come in because the wind's not always blowing and the sun's not always shining. So I always go back to the source. Climate change, what does that mean? Actually, it's the gases. And then how do we get rid of those emissions and all of the different human aspects and other aspects of our lives to solve it?
You talked about some really exciting uses for energy storage. So I wanted to ask you all, what are excited about in terms of discovery and development? Could we start with Johanna?
Sorry, can you repeat the question? I think you cut out.
What are you most excited about in terms of discovery and development?
So I think in the energy storage space, and I will talk from a battery person, the most exciting thing I am excited about, probably two things. Because first of all, batteries now work really well. We've designed them so they last a long time. You don't have to worry about buying an electric vehicle and your battery dying in 5 years. So we've sort of solved batteries. But what we haven't solved is how do we make batteries greener? And so batteries at the moment, the raw materials, the way that we're taking the raw materials out of the ground is not environmentally friendly, and it's also not socioeconomically friendly as well. So we are trying to design and discover more materials that produce greener batteries from the raw materials, abundant materials like sulfur, sort of is just a waste product. Can we make a battery out of that, or can we make a battery out of iron and essentially use rust as a battery? And then on the flip side of that, can we also figure out how to recycle the lithium-ion batteries that we have right now? And moving forward, as we're designing new batteries, can we simultaneously design how to recycle them? Because right now, none of our lithium-ion batteries are recycled. But lead batteries, for example, they're 90% recycled. So we can recycle batteries, but we don't right now have the technology to do it for lithium-ion batteries. So those are the two things that I'm most excited about.
John, if you want to answer that next, what are you most excited about discovery, within your research?
Sure. So cars, electric cars are pretty much under control. In general, there's a lot of improvements that are needed, but they're kind of under control. For NASA, we're interested in electric airplanes. And air vehicles are a completely different beast compared to cars, because you got to actually get it off. You can't, not only do you have to move it laterally, but you got to get it off the ground, these heavy things off the ground. So all the power and energy you need, and then to transport it, hundreds or thousands of miles. So the requirements for batteries for airplanes is dramatically higher than for cars. So, the energy storage need is like 2 or 3 times what we have for cars. And, increases in things like energy storage are incremental, few percent per year here and there. So to get to multiples like 2 and 3 times is a huge lift. And also safety, you can't thermal runaway, like Noel was talking about, is unacceptable if you're in the air. I mean, if you have it in a car, that's a bad day for sure, but at least you can pull over. But if you're at 20,000 feet and you have a thermal runaway event, that's catastrophic, right? So the safety requirements and the energy density, energy storage capacity requirements are dramatically higher, for air vehicles. And so it's going to take a lot of work to to achieve those goals. And we think that supercomputers and supercomputing, is maybe at the point where we can really accelerate some of that development. So working with people like Johanna, who has these amazingly detailed experimental capabilities, with our supercomputers. Actually, Johanna, you and I should talk offline maybe at sometime soon about maybe doing something together. I think these new, very cutting edge capabilities can really advance the field more quickly.
All right, and we have a couple minutes left. Noel, would you like to add on to that question?
Sure. I echo everything they said. I'm excited about all that stuff too. And maybe a few extra things is thinking about brand new chemistries for batteries. I mentioned how we invented lithium ion electrochemistry at Berkeley back in the 50s. Well, like in the last few years, we've developed a brand new chemistry called DRX, which is trying to solve the problem of not using cobalt or nickel in batteries. Like Johanna said, there's sometimes like supply chain issues with certain elements or environmental issues, or, the humanitarian part of who is actually responsible for digging that stuff out of the mines. And so we've developed this new chemistry that DOE is actually really excited about. And it is at a really high energy density, and it comes in dirt cheap. That's my joke, dirt cheap, because it has really easy elements to find here domestically. And so that's one thing, is just the fact that these labs are really great at doing the fundamental and basic research needed to do something like creating a completely new battery type. The other one I wanted to mention is artificial intelligence and machine learning. I think it might have been mentioned already, but just the fact that there's this quasi new technique and tool that we can use to advance our understanding of batteries and how we use them as well. So we've got teams that use AI/ML for energy storage and doing things like, helping understand how long a lifetime certain batteries, can go to, so that the financiers, the people who are actually going to help finance like demos and demonstrations and scaling this stuff up so it becomes a product for people to buy, have the certainty that these things are actually going to last for 20 years without us having to wait 20 years to see if they last. So that's just one example. But the fact that there's always new tools coming out that we can apply to make energy storage better is pretty exciting.
That's awesome, listening to all of these new technologies that many of our students might be working on in the future. And so we're going to wrap up now. So I have one last question. If you could all give some 30-second answers to. It's like, what recommendations or advice would you give to students who want to work in space or energy storage in the future? We could start off with John, and then Johanna, and end with Noel.
I think, just take thing about, batteries, which make it interesting is, you have to know a lot of different things. You have to know something about engineering, something about basic science, chemistry, physics, all these things. So really, nail your fundamental courses, your fundamental science and engineering courses. Make sure you have that great foundation, and then look for opportunities, to contribute, in companies or national labs, through internships, and look for your PhD advisors, before you go to grad school. That's something I think a lot of people don't do. Is if you want to do energy storage, find out who are the best energy storage researchers in the country, and then maybe reach out to them first, even before you apply to grad school, and then target those grad schools. So I target the professors first before the grad school, which is opposite of what most people, including me, did. So
I would just add that keep your options open. Don't pigeonhole yourself into what you think you want to do now. I think from all of our career trajectories and our paths, you can see that we sort of changed directions, and we didn't necessarily stay on a constant straight path. And so, there's never a point where you've closed all options off to yourself. So, you can always change the direction you want to go. But I do think I agree with John, like if you have the fundamentals of getting the classes of math and science and engineering early, then you're not cutting yourself off from those options later. And you can always change what you're studying, even halfway through your life.
as you can tell from my life, which is very different, basically every few years. So I had the very similar one to Johanna. I used to be very much like, I need to know exactly what I'm going to do. It's going to be astronaut, and here's the plan every year of how I'm going to get there. And then things started going like this. And basically what I tell folks now is, if you had told me at any point in my career what I would be doing 3 or 5 years from then, I would literally have laughed you out of the room. Like, what do you mean I'm going to be working at the White House? What do you mean I'm going to be running a center at a national lab? What do you mean I'm going to be doing energy storage? So like Johanna said, just keep your options open and keep going. And keep taking jobs that you really like and asking questions of people that you're interested by, and you're going to get somewhere really cool, and you're going to be given one of these talks in a few years.
Do what you love.
Thanks, Noel. Thanks, Johanna. Thanks, John, for joining us today. I want to remind everybody that you can go to the secret life of energy storage.lbl.gov to check out the full conversation with astronaut Kayla Barron, as well as the other field trips in energy storage. And thank you for introducing us. We have one last clip that we're going to show today that's going to be shared in just a second. But thank you all for being with us. And we look forward to next week when we will be talking about grid resilience, microgrids, and another dive into energy storage field trips. So have a great weekend, everybody. And with that, we're going to share our next clip.
It's so awesome to talk to you, and thanks for all of the awesome work that you're doing in support of our climate and energy storage, and hopefully also space exploration.
Station, this is Houston ACR. That concludes the event. Thank you.
Thank you to all the participants from Lawrence Berkeley National Laboratory. Station, we are now resuming operational audio.